Today we have to discuss the theory of coordination compounds. And the first theory is put forward by a famous scientist, Werner. And in his theory, which describes the formation and structure of complex compounds. That is, this theory describes with the formation and structure of a complex compound. And this theory is later termed as Werner's theory of coordination compounds. And due to this theory, he is awarded by Nobel Prize and he is also called the father of coordination chemistry. Let us explain what are the postulates of Werner's theory. The first point is every metal atom has two types of valency. First, primary valency, or it is also called ionizable valency, and secondary valency or non-ionizable valency. And second, the primary valency corresponds to oxidation state of the metal ion, and primary valency of the metal ion is always satisfied by negative ions. And third, secondary valency corresponds to coordination number of the metal ion, and secondary valency satisfied by either the negative ion or neutral molecules. Fourth, the molecules or ion that satisfy the secondary valencies are called ligands, and the ligands which satisfy the secondary valency secondary valency direct in space. So the secondary valencies are directional in nature, whereas primary valencies are non-directional in nature. And the ligands have unshared pair of electrons. These unshared pair of electrons are donated to the central metal ion and forming a coordination compounds. Let us explain these all points. That is, every metal has two types of valencies, primary valency and secondary valencies. Primary valency corresponds to oxidation state and secondary valency corresponds to coordination number. Let us explain these 2 points with an example. The structures of various cobalt amines are used for explaining the Werner's theory, and we know that cobalt has a primary valency. Primary valency means, I already told you that it is oxidation state. That is, cobalt has an oxidation state of 3 and it has a coordination number of 6. Always all metal has a fixed coordination number, and for cobalt it is 6. That means that its primary valency corresponds to 3 and secondary valency corresponds to 6. That is, primary valency corresponds to oxidation number. Here the oxidation number is 3. Therefore, in this case the primary valency corresponds to 3. And for cobalt, its coordination number is 6, and we know that for a metal, its secondary valency corresponds to coordination number. Therefore, in the case of cobalt, its secondary valency is 6. And here, the secondary valencies are represented by thick line, this line, and primary valencies are represented by dotted line. This dotted line represents primary valency and this solid line or thick line represents secondary valencies. And in this compound, that is COCl3 6NH3, in this compound all the secondary valency are satisfied by 6NH3 molecule, and the 3 chloride ions satisfy the primary valency. And we already told that the secondary valencies are directional in character. That is, these 6 NH3 molecules are occupy the corners of an octahedron. These 6 NH3 molecules are occupied in a corners of an octahedron. That is, it is directed along the space. That is called secondary valencies are directional in character. And these 3 Cl chloride molecules are non-directional. And in this case, the central ion, and the neutral molecules or ions satisfying secondary valencies are written in a square bracket. That is, central metal and all the secondary valencies. That means NH3 molecules are enclosed in a square bracket. And the primary valence is written outside the coordination sphere, and hence the complex may be written as CONH3 6 times Cl3. Here the coordination number 6 corresponds to secondary valency, and the 3, that is counter ion. We say that this is counter ion, and this 3 corresponds to primary valency. Okay. And also from Werner's theory, it is understood that the primary valencies are ionizable. That means this 3, the primary valency is 3 chloride ions, and these 3 chloride ions are ionizable. This can be explained by an experiment. That is, in this compound, when we add silver nitrate, to this compound, forming silver chloride, that is a white precipitate of silver chloride is formed. That means this 3 chloride ions combines with silver nitrate, forming 3 moles of silver chloride. That means primary valencies are ionizable. Whereas secondary valency, it will not give any precipitate, and therefore secondary valencies are non-ionizable. Okay, next we can take another example, that is COCl3 5NH3. COCl3 5NH3. From this structure, it is clear that out of 6 secondary valencies, 5 are occupied by NH3 molecules. That is, 5 corners of an octahedral are occupied by NH3 molecule, and 1 position is occupied by chloride ion. Here, the out of 6 secondary valency, 5 secondary valencies are occupied by NH3 molecules, and 1 chloride ion plays the double role of satisfying 1 primary valency and 1 secondary valency. That means out of 3 chloride ion, 1 chloride ion satisfy 1 secondary valency, and 2 chloride ions satisfy the primary valencies. This also we can test with an experiment when we add silver nitrate to this compound, forming 2 moles of silver chloride. That is, white precipitate is formed, silver chloride is precipitated, 2 moles of silver chloride is precipitated. That is, here 2 molecules of chloride ions are ionizable, and this chloride ion is non-ionizable, which satisfy the secondary valency and which is non-ionizable. Only 2 chloride ions are ionizable and forming 2 Cl minus, that is 2 molecules of chloride ions are formed in solution, and only these chloride ions are combined with the silver nitrate to precipitate silver chloride. Now we take another example, that is COCl3 4NH3. Here only 4 molecules of NH3 are there, and in this all the 4 corners of an octahedral are occupied by NH3 molecule, and the other 2 corners of this octahedral are occupied by chloride ion, and here only the primary valency is 1. That means chloride play both role, that is primary valency and secondary valency, and it dissolve in a solution forming only one molecule of chloride ion. That means one molecule of silver chloride is precipitated when the addition of silver nitrate. Next example is COCl3 3NH3. COCl3 3NH3. Here only 3 molecules of NH3 are there. Therefore, all the chloride ions occupy the secondary valencies, and we have to written the formula of this compound like this: COCl3 NH3 thrice. There is no counter ion and there is no primary valency, and here all the chlorine ion play the role of primary valency and secondary valency. And here when we add silver nitrate, there is no precipitate is formed, because in this case these chloride ions are non-ionizable because it satisfies the secondary valency, and it is non-ionizable and it does not form any precipitate with silver chloride. That's all about Werner's theory. Let us conclude this. Once more, I told you all the postulates of Werner's theory, and let us understand very clearly. Every metal atom has two types of valency: primary valency and secondary valency. Primary valency is ionizable and secondary valency is non-ionizable, and the primary valency corresponds to oxidation state of metal ion, and primary valency of metal ion is satisfied by negative ions. Only negative ions satisfy the primary valency, and secondary valency corresponds to coordination number, and the secondary valency may be satisfied by either negative ion or neutral molecules. That may be ligands, may be negatively charged ligands or neutral molecule. And the molecules or ions that satisfy secondary valency are called ligands, and ligands which satisfy secondary valencies must project in a definite direction in space, and so that secondary valencies are directional in nature, whereas primary valencies are non-directional in nature. And the ligands have unshared pair of electrons, and these unshared pair of electrons are donated to the central metal ion, forming coordination compounds. That's all about Werner's theory. The main limitations of Werner's theory are: it fails to explain why all elements don't form coordination compounds. Not all elements forming coordination compound, and it cannot explain why all the elements don't form coordination compound. And also it fails to explain the directional properties of bonds in coordination compound. It does not explain the directional properties of bonds, and it does not explain the color. Most of the coordination complex are colored, but Werner's theory cannot explain why the complex is colored. And the magnetic and optical properties are shown by coordination compound, and also the coordination compound show magnetic behavior. Paramagnetic and diamagnetic behavior are shown by the coordination compound, and Werner's theory cannot explain the magnetic and optical behavior of coordination compound. That's all about Werner's theory. Thank you.